In the previous videos, we had a look at several different types of pre-processing techniques. Have a look at them up top here. If we want to look at outliers, that is the focus of this video. What are outliers? Well, basically, they are data points that significantly deviate from the bulk or the mean of the dataset. Outliers can be problematic because they can skew your statistics, specifically your mean calculation. But sometimes outliers are not necessarily bad data points because they would reflect the truth. They would reflect the actual value that the outlier supposedly indicates. So one must be very careful as to how you deal with outliers. Sometimes you delete them, other times you keep them in your dataset when you analyze the data, but at the same time, keep in mind that you have these outliers. So one has to take a balanced view and weigh up all the pros and cons of the outliers. The way that I normally deal with the outliers is I keep them there unless there's a very obvious reason that the cell or the element in the data set is absolutely incorrect. What that means then is when I analyze the data or when I visualize the data, I must be acutely aware of those outliers. So when we go back to the data, you can see that I've run all the files up top here. And we are now at this section on dealing with outliers with regards to the test cricket data for South African players since 1991. Firstly, I'll give a brief explanation of what outliers are, but let's have a simple visualization of a box plot. I have now used Seaborn to visualize a box plot for specifically the balls column. But notice there is an error. And the reason that there is an error is because balls is not a numeric data type. Now that doesn't make sense because balls should be a numeric data type because balls are the number of balls bowled by a bowler. There's something wrong with that balls column. So what I'm going to do now is I am going to create a placeholder where I select only the integers as well as the floats in the respective columns, and I print whether or not they are numerical columns. So Shift Enter, and you'll see that it lists all of these columns as numerical. You would expect balls to be there because it's a numerical value. So let's just put that on the back burner for a moment. Let's now plot box plots for only these identified numerical columns. As you can see, if you look at the data, a good idea might just be to widen the x-axis a little. So let's run the next code, and what I do there is I play around a bit with these values on the x-axis. On the top over here, you can see the range was till about 450 odd, but on this new line of code, it goes up to 500. So it extends a little bit to the right. Let's now look at these box plots. Now what you'll notice is all of these are pretty much on the left-hand side, close to the y-axis, because they all start at 0, or at least 1. For example, matches. You won't have a cricketer that is on the data frame that has not played a match. Obviously, they would have played a match. The minimum value would be 1. Some of them can be 0 because some cricketers have not bowled. Some cricketers do not have 10 wickets in a match. Some cricketers do not have wickets taken. So you would expect the left-hand side of this box plot to be on the y-axis, on the 0. So let's say we want to extend the x-axis a little bit more to the left. So we can take this code, or you can use this existing code, and you can alter that 0 over there to a minus whatever. But for our purposes, let's just add that line of code. So I'll go to that line over there, and I press A. And if I press A, a new line of code opens. And then I just paste the code in there. And then instead of having a 0, I can have a minus 20. Now I know the minimum value is going to be 0. So nothing will be in the negative value range. So Shift Enter. And that's clearly visible over here. Now some of them will start at 1 because you would expect, for example, the number of matches played. Let's just look at what these box plots are. They are often also called box and whisker plots. You can see there's a box and then there's sort of a whisker. Now, normally you would have a whisker on the left-hand side of the boxes as well, but in this case you don't. The box itself reflects what we call the interquartile range. And the interquartile range encompasses 50% of the data. So the bottom of the box on the left-hand side is quartile 1, which is 25% of the data. The right-hand side of the box in this case is the 75th percentile. And the difference between those two, in this case now the blue shaded box, is the 50% of the data. The median is reflected by the line inside the box. And then the whiskers represent 1.5 times the IQR, the interquartile range. So what this means is All the values outside this whisker, this line over here, are outliers. So we can get a sense here of what the outliers are. And you'll notice in terms of matches, there are some clear outliers. Innings bowled. There are quite a few bowlers that have bowled noticeably more. There are also quite a few bowlers that have noticeably more wickets. There aren't bowlers that have noticeably more wickets as the best wickets in an innings. In terms of runs that is attached to the wickets taken, there is one outlier. Nothing in terms of best bowling per match. There's one in terms of runs. I'd suspect that would probably be the same cricketer. In terms of the economy rate in the matches, there doesn't seem to be anything noticeable over there. Maybe you want to plot it vertically instead of horizontally. You use this code over here, but then you'll notice the scale is not appropriate. So we can adjust the scale by using the code over there, and now the scale is appropriate. You might want to tweak the x-axis a bit here. You can play around with numbers over here because the names of the columns are quite long. So play around with it. So these are different ways that you can visualize or get a sense for whether or not there are outliers in the data. Of course, we haven't looked at its specific examples yet. We're just getting a sense right now. Here I'll give a nice explanation of what the box plots are. Let's now look at a scatter plot to see if there are potential outliers. Matches versus innings bat. So in other words, on the y-axis, you've got the number of innings batted, and then on the x-axis, you have the number of matches. In terms of the number of matches and the number of innings batted, you would expect that the more matches you have played, the more innings you have batted. I know, for example, if we look at matches played, I know that Jacques Kallis has played 165 odd test matches. So we are looking at a value around about there, and that means that he has, there he is over there, he has batted 278 times. So he's played about 165 test matches. He has batted 278 innings within those 165 odd test matches. That would probably in the context of this be somewhat of an outlier because he is noticeably more than the second most number of matches, which is that one over there. Let's now specifically test for outliers. Besides the visual representation or the visual depiction of the outliers, you can get a sense of them. Let's look at two specific statistical measures. The first one is the Z-score, and the Z-score is basically a threshold that you decide on, which is set at a certain number of standard deviations away from the mean. Typically, the common practice is to use 3 standard deviations away from the mean. What that means is you're looking at about 97.5% of all the data, and anything that is beyond that, 97.5% of the data, would then be regarded as your outlier. So in terms of interpreting it, if you've got a Z-score that is 0, it lies exactly on the mean. If you've got a Z-score that is 3, it's 3 standard deviations away, etc., etc. If the Z-score is positive, the data point is above the mean. If the Z-score is negative, the data point is below the mean. So let's import some libraries now that will enable us to conduct these statistical measures. And for that, we import the SciPy or Skippy, the stats part within that library. We know we already have NumPy, so I'll just repeat it over here. We're going to use the Z-score to calculate the Z-score from this data frame over here. You can see there's an error. And the reason there's an error is because the Z-score only uses numerical data. And some of the columns in the data set are not numerical data. So what we need to do then is we need to identify the columns that are numerical data and apply the Z-score to only those columns. So we run that code. You can see here are the Z-scores. So remember up here, I'll give you a nice explanation. The larger the Z-score, the further away the data point is from the mean. If it's smaller than -3 times away or greater than 3 times away, we will then regard that as an outlier. So just quickly scanning the data. Remember now, it only lists here the head, the top 5, and the bottom 5. And if you quickly look over here, you'll notice here is a value that is an outlier, and that is associated with the wickets for cricketer number 2. So if we quickly scroll up and we go look at the name of cricketer number 2, it's Alan Donald, and his wickets are 330. Why is that an important little thing to check up on? If you look at the Z-score, you will notice that it's 3.4, so it is a reasonable way above 3. If Alan Donald has 330 test wickets, it probably means that if you run this code, an outlier will be defined in terms of wickets now, according to a value that is probably somewhere around 300. If 330 is calculated to have a Z-score of 3.4, then I can get a sense that an outlier would be defined as a value, or the threshold as an outlier value, probably be around 300, 305, 310, somewhere around there. So in the back of my head, when I look at the wickets column, I have a sense of what can be regarded as an outlier. And because of my domain knowledge, I would know then, or have a sense of, that there are only 5 or 6 cricketers that would have test wickets of more than about 300, 310. So if I delete the outliers from the wickets column, there would probably be 5 or 6 or 7, somewhere around there. The question is, should I delete those outliers? I know that Dale Steyn has got the most wickets of all the cricketers. He's got 439, followed by Sean Pollock, 421. Why must I exclude them? It doesn't make sense to exclude them. The highest value of 439 and Sean Pollock's value of 421, they are real data, and there's no reason why I need to exclude them. If you look at a few other columns, just quickly, here's another one, 10 wickets in a match. Again, you can see, number 2, it's again Alan Donald. So the number of times Alan Donald has had 10 wickets in a match would, according to the definition of the Z-score now being 3 standard deviations away from the mean, be regarded as an outlier. Would it be sensible to leave out Alan Donald then? Absolutely not. So that's in terms of the wickets. Now this output doesn't show all the rows. Let's add all the rows. So here's Alan Donald again. You can see the innings bowled. It's very close to 3. The wickets is over 3. Anything else over here? There are a few that are 1s. Remember now these columns over here are numerical values, and most of them are related to the bowling figures. Here's a value over here, 4.671. Cricketer number 33. That will definitely be regarded as an outlier. So if I go back to the top, you can see who's cricketer number 33? Dale Steyn, 439 wickets. So again, that's above 300 odd. Let's now set a threshold, because we've calculated the Z-scores, but we haven't actually set the threshold which allows us to identify the cases or the rows that are outliers. So I give a threshold of 3, and then I use this line of code over here where I say indicate the case numbers if the threshold of 3 is exceeded. In other words, if the Z-score is greater than the threshold. Now you can see what it lists over here are 2 arrays. The first array consists of the rows where the Z-score exceeds the threshold. The second array contains the columns where the threshold is exceeded by the Z-score. Now that's great. So you would then look in the first one, for example, you'd look in row 2, column 2. Let's now give this function over here where the thresholds are exceeded, the code for that. Let's call it this row indices, comma, column indices. We run the code, and now we run this code over here to be a bit more specific. In other words, what it's doing is it takes this input cell number 110 and it just makes it easier to interpret. So what these lines of code do is it identifies the outliers by looking at the specific values, and then it tries to convert them to numerical values if they are convertible. If they are convertible, it will show you the actual conversion over there and where it is exactly. But if it's not convertible, it will indicate that it's not a numeric value. Let's now plot 2 histograms to get an idea of whether or not the Z-transformed normal data, which is what I did over there, and the Z-transformed log normal data. What you can notice here is that you would expect the normal data to be normally distributed more or less. In other words, close to the mean, but not necessarily for the log normal data. The fact that there are some negative values, you can see it's less than 0, means that there are some data points below the mean. This means that there are some data points that are moderately lower than the average or the mean. We're getting a sense of the outliers, and we will decide what we're going to do with them. The next statistical measure to assess whether or not there are outliers is what we call the interquartile range. Now, the interquartile range is calculated by the difference between the third quartile, Q3, and the second quartile. In other words, it represents the range of the middle 50% of the data. And if you can recall those box plots we did earlier, it's the actual box itself. And the one side of the box is Q3, and the other side is Q1. So the difference between them would be the 50% of the data. Let's then set these thresholds. I run this code over here, and what I do is I select only the numerical values, we know that, those that are floats and integers, and I calculate Q1 being the numeric data, as indicated up there, dot quantile, that is the pre-written code, and I set it to a value of 25%, 0.25, For Q3, I assign it to a value of 0.75, which is 75%. The IQR is equal to Q3 minus Q1. And if you get that over here, and then you print that, you get the output over here. So the interpretation of this means, if you look at active years, the value is 6. This means the IQR for the column active years is 6, which means that 50% of the values in active years fall within the range of 6. So in other words, if I had to take Q3 and Q1 as the threshold of the box and the box plots, the range between Q1 and Q3 will be 6, which means that 50% of the data lies within that range. If you look at matches, for example, the range will be 35. So the difference between Q1 or Q3 rather and Q1 will be 35, and 50% of the data will be in that range. So if I want to calculate the whiskers, I would use this code over here. I've already run it, and if you notice at the bottom here, it's picking up that there are certain columns that are not numeric that you would expect to be numeric. That might be a problem going forward. It also lists at row 105 that there are values that exceed the threshold. But overall, if you look at the data, there aren't really many concerns with regards to the outliers. There aren't values that stand out necessarily that are problematic. So I have decided with regards to the outliers that I will leave the outliers. They are not wrong data, and they are reflective of the actual data given domain knowledge. You could decide to delete them. The rule of thumb is delete them if the outlier is incorrect data. Sometimes the outlier will be correct data, but it's so far away from the other observations that it might warrant deleting it, even though it is true data. Think about it. You've got to know your data and have sufficient domain knowledge to understand what you're doing and why you're doing it. In the next video, we will look at additional problems with regards to data, and especially this problem over here that we've seemed to have identified, where there are certain rows and columns that are non-numeric.